Lecture number 6, the Rankine cycle, and today we'll be using the HS diagram for the Rankine cycle, solving the problem in a Rankine cycle. Let's have a problem statement first, and then we will be learning about the HS diagram. Water is a working fluid in an ideal Rankine cycle with the reheat. Superheat vapor enter the turbine at 10 megapascal, 480 degrees centigrade, and a condenser pressure of 6 kilopascal. Steam expands to the first stage of the turbine to 0.7 megapascal, and then it is reheated to 480 degrees centigrade. Determine the cycle for the cycle. The rate of heat addition in kilojoule per kg, the thermal efficiency, and the heat rate transfer from the working fluid passing through a condenser. So if we are using like a steam table, so we will be using, for example, we will be looking at the 10 megapascal and 480 degrees centigrade. Then we would realize like it will lie in a superheated condition, and then we'll be using the superheated steam table. And from the superheated steam table, we will try to find the enthalpy H and entropy for this state. Then we will be expanding from state 1 to 2 isentropically, and then for at state 2 we will be trying to just find out like whether if it is inside the vapor dome or outside the vapor dome. If it is inside the vapor dome, which may case in this case maybe, we will try to find the value of x over here, and then we will be finding the value of h2 from here. Then we will be reheating it, and then reheating it to 480 degrees centigrade. Then for 480 degrees centigrade, we will be again checking in the steam table, and that would be finding from the superheated steam table. We will be finding enthalpy H3 and entropy S3 as well. And now expanding back to state number 4, and at state number 4 we again will be checking like whether it will be lying inside the vapor dome or outside the vapor dome. If it is inside the vapor dome, we will be finding as x4, then we will be finding h4, and then obviously we will be finding the if we need to find the thermal efficiency or mass flow rate, so using these enthalpy and so on and so forth, we will finding those things. Now this is the way when we are dealing with the when we are dealing in steam table. Now what about the HS diagram? Now as the name suggests, so HS diagram, so there would be two coordinates of it. So one of them would be enthalpy H over here, and entropy S. So HS diagram would mean like we will be enthalpy and entropy diagram. It is mostly referred as a Mollier diagram uh, from the maker of, I would say, like from where it came from. So it is called as HS diagram or Mollier diagram. So that means like we will be having two coordinates, enthalpy coordinates H and entropy coordinates S over here. Make sure you check the units of enthalpy and entropy from these agents. Now, if I just look at the HS diagram itself, there are number of line actually in this diagram. So let's check one by one which diagram represent what thing. So if you just check this thing, like over here, a distinct line, these curved line over here, and if I just make it complete, so it will make sense, like it seemed like a vapor dome. So these lines are my saturation line, or in other words, these are my saturation vapor line over here. At saturation vapor line, the value of x, or which I mean like dryness fraction, that would be equal to 1. So I have got a line of 1 over here somewhere, this one. Now if I move inside the vapor dome, the value of x would decrease. So I have got different lines over here, 0.95, 0.90, 0.985 and 80, and obviously there are a number of other lines which are passing in parallel to these lines. So these are our saturation line. Now the other major distinct line which actually you can see are these big lines over here. So these lines are the my pressure line. Now if you can imagine, like in a vapor dome, normally the pressure line are something like this. If I would just lay like somewhere here and then over here. So these are the pressure line. And but the in Mollier diagram or a HS diagram, the figure is skewed or the figure is tilted in such a way, like the parallel pressure line, they are going straight inside the vapor dome, so it is a little bit tilted or a little bit skewed as well. So that mean like the pressure line seems to go straight into the inside the vapor dome. So these are our pressure line going straight inside the vapor dome. Now the other lines, and yeah, obviously yes, you can imagine like these are the distinct pressure on which the pressure values are given over here, and these are the other pressure, small pressure, and you can actually find it from these values. Now there are other lines, like for example these lines over here, you can just check it, like on the top of the lines there are some values given, and that mean like these are the temperature lines. And yes, these temperature, similarly the temperature uh, lines are also divided in sublines as well. So 3 to 4 distant line what we have seen over here, these are the saturation line, and these inside the vapor dome we can actually find the saturation line at different dryness fraction. These are our pressure lines, and these are our temperature lines which are moving in a horizontal, and then obviously going inside the vapor dome. Now even if you can check the temperature line, if you can imagine, you can not find the temperature line going inside the vapor dome. Let me rub it out for some of them, so you just check it, you can see clearly. So like that mean like if I just check this line over here, which is the temperature line, this temperature line just end on a saturation line over here. So just say like I said like these are the pressure line which is going straight inside the vapor dome. Now, if you can imagine, like inside the vapor dome, the temperature line and pressure line, they are both parallel. So whatever the line of pressure is over here inside the vapor dome, so these are also we can also just regard it as a temperature line as well. So inside the vapor dome, you can find the temperature. If it is inside the vapor dome, you can find the temperature from the pressure line as well. So they are different things. And yes, in Mollier diagram you can find the different Mollier diagram as well. You can find the specific volume in line as well in different Mollier diagram. In this particular Mollier diagram which actually I've shown you over here, no, we can there isn't any specific volume line, but yes, you can find the Mollier diagram with the specific volume lines as well. um, Now let's move to like specific the enthalpy over here. Let's say for example one of them over here. So these lines are divided in different gradients now. So 3200, let's say for example 3300 over here. So that means like the line inside between them should be 3250 something. And if I just divide it further, so that means like that would be 3275 something, and so on and so forth. So you can divide with precisely, and or with the ruler, so you can just divide these line anyway. And that goes for the entropy as well. So but at the bottom you can find it like entropy of 5.5, 6.0. So that means like that this line would be 5.6, 5.7, 5.8, 5.9, and yeah, obviously 6.0. So that means like you can actually divide it differently. Now let's move to the question. So we can actually try to solve the same question on a Mollier diagram. Now let's have this thing. Let's say for example, let's say like again, I would read out water, working fluid, uh, an ideal Rankine cycle with a reheat. The first condition is like we have got a superheated vapor at 10 megapascal, 480 degrees centigrade. then it is expanded to 0.7 megapascal. Um, sorry, 0.7 megapascal. From 0.7 on a 0.7 megapascal, it is then reheated to 480 degrees centigrade. Then it is further expanded to a condenser pressure of 6 kilopascal. I explained earlier, if we were using the steam table, so what would be the step involved? Let's move to the HS diagram. If we want to use the HS diagram, what should be the step involved, or what, how can we solve the this question using HS diagram? So as explained earlier, in a HS diagram, we would be having a pressure line and we would be having a temperature line over here. So let's find the pressure of at state 1. We were having a pressure of 10 megapascal and a temperature of 480 degrees centigrade. So let's find the pressure of 10 megapascal and a temperature of 400 degrees centigrade. So you can just check it like over here. We have got different pressure over here, and then this pressure is at this point is pressure of 10 megapascal. So this is my pressure, 10 megapascal. Now coming to the temperature line. So temperature over here is somewhere here is 450 degrees centigrade. So from 10 megapascal 480 degrees centigrade, so I'm following this line 450 and I'm following this line, so that means like 450, 60, 70 and 80. So at this point, this is my 10 megapascal state number 1, 10 megapascal and 480 degrees centigrade. Sorry for simplicity of this lecture. I've already drawn these line on a HS diagram using like different color. So let's say, but yes, I would explain it anyway. So that means like this is by 10 megapascal and 480 degrees centigrade. So now checking the enthalpy over here. 3 The enthalpy at this point is 3300. Enthalpy over here is somewhere like 3350. So if I divide it further, so that means like there would be enthalpy of 3325. So what I'm assuming, like enthalpy at this point, at this yellow point, might be 3324 something. So we will check it later on with the stream table anyway. So that means like I would say like not precisely, but I would say like the enthalpy at this point 10 megapascal and 480 degrees centigrade, enthalpy is 3324. Now moving down to the entropy. So entropy over here is 6.5, 6.6, 6.7, 8, 9 and so on and so forth. So that means like 6.5, if I'll just say like over here, so that means like it would be 6.5, let's say like 6.5 25 something, or let's say, yeah, that might be okay actually. So 6.5 to 5. So that means like entropy would be 6.5 to 5 something. I would as I said, like that is a little bit rougher estimate. You can precisely do it when you are solving this example anyway. So this is at state 1, the entropy H1 is 3324 and enthalpy is 3324 and entropy is 6.525. Now it's like we are expanding to the state 2, expanded to state 2, which is having a pressure of 0.7 megapascal, and we have got the condition in which entropy S1 is equal to entropy S2. So isentropic process. S1 is equal to entropy S2, but the pressure is 0.7 megapascal. So now moving to this again HS diagram. So that means like 0.5 is over here, 1 is over here, 1 megapascal is here. So let's check, let's count it again. So 0.5, 0.6, 0.7, 8, 9, and obviously this one. So the second line, which is over this line seems to be 0.7 megapascal. So 0.7 megapascal, and the same entropy, if I would say, so this line is 0.7 megapascal and entropy over here. So just dropping the entropy from this point to this point, sorry for the line actually. So entropy dropping from state 1 to state 2, I have got the point which is coinciding at 0.7 megapascal. So now again, checking the enthalpy over here. So that might be not so much visible over here, but anyway, over this point. So I have got 2600 over here, 2650 over here somewhere. So if I just check it from this side, 2600, 2650, and that should be 2700. Say if I would just say like roughly, it would be 2685 something. So let's check it later on, like what would be our major, or what would be our exact value of enthalpy. But roughly, if I would say like it should be nearly 2685 something. Now it's a like in the same manner, it's a like we are having the reheat process. So that means like in the reheat process, the pressure remain constant while the temperature is increasing. So if pressure remain constant, temperature is increasing. So temperature is increased to 480. So that means like 460, 70, and 80. So that means like this line is actually a line of 480 over here. Yes, so this point is 480. So that means like this is my point 3. Point 3 is 0.7 megapascal and a temperature of 400 degrees centigrade. So now at point 3, 0.7 megapascal, 480 degrees centigrade, if you can check it, so that means like it would be, uh, let's say for example, 3400, 3450. So I can just simply say like 3440 something. So that means like it can be one of a value which would be near to the 3440. So that we have solved it again another point. So state number 1 to 2, then from 2 to 3, and then back to, let's say, state number from sorry again dropping in a second stage of the turbine from 3 to 4. So when we are going from 3 to 4, it's a pressure of condenser pressure, which is, sorry, it's a condenser pressure and a condenser pressure of 6 kilopascal. So at 6 kilopascal, we are having the entropy S3 is equal to S4 over here. So, and a condenser pressure of 0.006. Now, 006 mean like 6 kilopascal. So that is 0.004. If just like let me try it again, 0.004, 005, 6, 7, 8, 9, and so on. So that's correct actually. So if I'm saying 04, 05, 06, so this line, particularly this line over here, is my 0.006, and entropy S3 is equal to S4. Sorry, we did not check the entropy for state 3. So let me select 6, 7, 6, 7, 7, 7, 8, and 7, 8, 9, and that is 80. So that means like that could be roughly equal to 0.78 something. Uh, sorry, that means like 6, 7, 8, 8, 8, 8 something. I would say like 7.88 something. So that's what actually entropy would be for the state 3, and entropy S3 is equal to S4. So now for the state 4, we can find the enthalpy. So that enthalpy over here would be 24, 25 something, and sorry, 245, 2450 something. And over here, if I can imagine like 2426 something, if I say that 2426, if I just say. So enthalpy would be 2426. Entropy would be 7.88. And even if you are a little bit more curious, like you can find the value of x as well. So you can find the value of x over here as well. Like this line over here is 0x is equal to 0.95. So that means like at this point 0.95. So 0.95. So 0.95. So 0.96 and 962, let's suppose. So x is equal to 0.962 at state, x2 is equal to 0.962. At, let's suppose, state 4, we would be having the value of x is 0.90, 91, 92, 93, and 94 something. So 941, if I would just say like 942, x4 is equal to 0.942. Anyway, like you have already got the enthalpy, so you do not need the value of x anyway. That would be needed if you were solving it by the steam table, while in the Mollier diagram or HS diagram, you can find it directly. So that means let's rewind it. So that means like at state 1 we are having enthalpy of 3324 and entropy of 6.525. At state 2 we are having the enthalpy of 2685 and entropy of same 6.525, and let's say x value of x is equal to 0.962. At state number 3 we are having the enthalpy of 3.3440 and having the entropy which is equal to 7.88. At state number 4 over here we are having the enthalpy of 2426 and entropy of 7.88. So let's check with the solve example or the solve numerical, which already we have been given. So and yeah, that being solved, on a steam table. So let's check our value with the steam table value anyway. So let's check state 1. So state 1 was 3321.4. Just say like 332224 something. If I just check it again over here, so that means like it was state 1 was 3324. So yes, we are a little bit near to it. So state 1 is 3321.4, and the entropy is 6.55282, and what we were having like over here 6.525. So almost near to that one. At state 2 the value of x, which we do not need it anyway, was 0.9619, and over here we did calculate like the value of x as, oh sorry, we find the value of x at 0.962, which is definitely equal. The enthalpy over here we did find at state 2 was 2685, and over here in from the steam table we did 2684.8, so we were almost near to it. At state 3 the our enthalpy over here is 3438.9. Over here we did say like 3440, which is almost anyway same. And the value of entropy was 7.88 in that case, from HS diagram, and over here it is 7.8723. The value of x4 was 0.9413. I hope we did it right something. Sorry for that. So yes, it is 0.942 anyway. The value of enthalpy is 2426, and over here the value of enthalpy is 2425.6. So obviously if you can just check it from the steam table, and you can just using the Mollier diagram, so it is almost 98% correct. And obviously you can find it like you will have a little bit difference in the last value anyway, which would be I would say like acceptable value. So that means like using the HS diagram, you can solve this example very quickly and you can solve the problem very quickly. Now it's up to you in an exam right now, in exam period, like which method you are using. But I normally find the HS diagram mostly easy, mostly quick. But if you are looking for the accuracy, so the steam table are more accurate. And also, like, if now moving to the other part, if I'm saying like, let's say state number 5. So state number 5 is actually at the saturation vapor state, sorry, saturation liquid state. Now if you can check the Mollier diagram over here, so we do not have got the saturation vapor state over here, so something like this. So that's why it is not over here. If you can just check the lines over here, so when you are moving towards the vapor dome and obviously towards the saturation liquid side of a vapor dome, the line itself actually are squeezing too much, and you can find like you can actually a little bit you cannot differentiate between two different lines. So it is most advisable, even this diagram is not actually full in the, or it's not actually complete in terms of saturated liquid state. But if you can find the Mollier diagram, which actually show you the saturation liquid state, and even in that case, I would not recommend you use the Mollier diagram for it. You can simply use the steam table for the saturation state. Now, I hope like you understand the whole question. The other part is quite simple. You can solve it like from the same um, notes. But yes, it was the lecture about the using of the HS or HS diagram, or what we call it as Mollier diagram. Have a nice time. If you have got any question, you can post it on a Google Classroom. Thank you very much.